So today we will talk about one of the strangest and rarest German calculators, namely the Adsumudi. The Adsumudi was conceived in 1907 and it operates according to a principle that is radically different from any other calculator that was ever sold, to my knowledge. So if we just look at the top plate, what we see is an input register over here with 10 inputs. We see an input control register, so if we put anything in the input, it appears immediately in the input control. We have a reset button for the input, like this. We have a totalizer register at the top, so if we set something in the input, for example 648, and we operate the machine, which is done by pushing and pulling this lever. And you see that the 648 appears in the result, and at the same time the input register is reset. So the number is really transferred from the input to the result, and this is of course a challenge, especially if you want to do repeated additions or repeated subtractions, like for multiplication or division, because you lose your input every time you make an operation. We have a zeroizing button for the totalizer over here, and about this register we'll talk in a bit. So this is of course a problem. Another problem is subtraction, and so the way that the machine operates is like this. It has racks on either side of a slot, and the gear wheel that is connected to the result register is in the middle, not touching either rack, and then depending on which way the carriage shifts, to the right or to the left, the machine will either add or subtract. So if we add, as you can see, the carriage shifts slightly to the right. So the question is now how to get it to shift to the left and subtract, because there does not appear to be any control in the machine that allows you to do this. Luckily, the patent specifies how you need to do this, and the way to do it is simply by taking the operating knob and clicking it to the right. So you now see an S in this window as opposed to an A for subtraction. So it just has a click action allowing you to choose between subtraction and addition. So if we put 1 in the register and we add, you see that the register moves to the right. If we switch it to subtract and put 2 in the register, then we'll see that it'll subtract 2 from 1 and we'll end up with all 9s in the result register. And you can immediately see how the tens carry is operating, because to the result register are connected levers, which will then, if it passes over 0 or from 0 to 9, it will click to the side and allow the setting lever in the next position to go to -1, and if it goes to -1 and it is engaged with the result register, then it will just do the tens carry in that way. So there we go. This is adding and subtracting with the Adsumudi. But of course, the thing is called add, su, mu for multiply, d for division. So there must be a sensible way to multiply and divide with this thing. One more thing before we get to the multiplication and the division, that is the memory register. So the Adsumudi also has a memory, which is this register, which we haven't talked about yet, because it's essentially not connected to anything on the machine, but you can connect it by pushing this Umschaltung button. You can connect it, and then if you reset your totalizer, then the result from the totalizer will come back into the memory register. And of course there is a zeroizing lever for the memory register as well. So you can keep totals of, for example, sums of multiplications, if you know how to do multiplication. Now, because the input disappears every time you do an operation, you would need something that allows you to reset the input every time. And the machine comes with such a tool, which is this carriage that is delivered together with the machine. There we go. And so this thing has setting levers which are fixed. As soon as you set them, they don't spring back. So we set, for example, 135 on this end of the carriage, and then if we push it down, it will set 135 in the setting register. We can click it to the operating lever, turn it to addition, and then we have this bar which we can simply use to repeat add 135 to the totalizer. So that's 5 times. Well, we're halfway our 5th addition. The addition has happened, but we still need to put the machine back into the setting position. So before we do that, we can also shift this carriage, because it is an actual multiplying carriage. If we push down on this bar, we can actually shift it to the next position. We do need to remember to write down what we have multiplied, because of course what the machine does not have, and which is a real pain in the ass, is a counter register. So what we want to do is write down 5 as the multiplier, and so now we'll do it again. We put it down to the setting position, then we go 1, 2, 3. Let's stop at 3. We move the carriage, so it indicates here which position it is in, and then we can do, for example, 6. 1, 2, 3, 4, 5, 6. Easy. So now we have the total, which is hidden under the carriage. And what we can do now is reset the setting, or the supplemental setting register, by pushing this button and then pulling the carriage down, which will reset it to 0. We can then unhook it, shift it to the top, and we can see our result here. 135 times 635 appears to be 85,725. Division is done in the same way, but then by subtracting. So we can add this while we're at it. We can just as well add it to the memory register. There we go. So what we do for division, if we are trying to divide, for example, 437, we can set it at this end, put it on add. It's in the register on the left side, and then we can set our carriage. We can set 21 if that is what we want to divide by. And then we can pull it down, which sets 21 in the entry register. We can put it on subtract, and then we need to keep a really close eye on what exactly we are doing, because again we are going to be writing down, this is from the previous time, but we are going to be writing down our numbers as we subtract them. And we see right now that we have 43 over here, 21 down here. So that means we can subtract at least once. We're down to 22. We can subtract again. That is 2. We write this down. 2. And then we shift the carriage. We need to do this with the carriage in the top position, because otherwise the setting levers foul the setting slides that come down from the carriage. So we'll move it over into position 2, and then we'll bring it back down. And immediately we see we're in trouble, because we have 17 up here and 21 down here, so it will actually have an underflow, and that is not what we want. So that means that we actually need to write down a 0 over here. We can subtract it. We can then add it again. And while we're in the top position, we can shift the carriage to the next position and bring it back down. So now we have, instead of 17, 170. We have 21 here, and we can start subtracting and keep an eye on the numbers. 149, 128, 107, 68, 65, 44, 23. We have 21 here. We can do one more. And then we need to shift the carriage. And if I would have counted, which you need to do, then I would know that we now have 8 subtractions. Put it down, and we see that we have 21, but here we have 20. So that means our next number is 0. And then we need to subtract. We need to add again and move the carriage. There we go. Put it back on subtraction. We now have 221 down here, so we can go 1, 2, 3, 4, 5, 6, 7, 8. We can do one more, 9. And then we shift the carriage. We now have 110 for 21. 1, 2, 3, 4, 5. I shouldn't have done that. It should have stayed in the upper position. So what we need to do is now subtract one more time. Will affect the tens carry. Then we add one more time, again affect the tens carry, and then not forget to shift to the next position and put it back to subtract. So we now have 21 and 50. That should be 1, 2, shift the carriage. We now have 80, so that leads to 1, 2, 3. Shift the carriage to the last possible position. This is 170, so 1, 2, 3, 4, 5, 6, 7, 8. 8, and then I would continue shifting. But so here is the result. 437 divided by 21 should be 20.809238. Easy as pie, but it would be a lot easier if the machine would have had a counter register of some kind, which frankly doesn't seem so difficult to implement. You just need a counter that counts the number of times you move the handle. Preferentially, this would be added to this carriage over here, and then the machine would operate like any other calculating machine, which would give you easy access to the results as opposed to having to write them down digit by digit. So it is clear from this explanation why the machine was not that much of a success. It's a bit cumbersome, it's a bit tiresome, it's a bit difficult, it doesn't take all your worries with regard to calculation away, but at least it functions and it is a beautiful piece of mechanical engineering, which is also, and also because it's so rare, why it is so sought after these days. I hope you enjoyed this, and see you next time.